Okay, so in this video we're going to be talking about VSEPR theory and molecular geometry. Before we get started with it, this goes back to drawing Lewis structures, so it's an extension of that topic from previous video. So what is VSEPR theory and what is molecular geometry? So VSEPR theory is what VSEPR stands for is valence, shell, electron, pair, repulsion. So what does that mean? When we talk about a Lewis structure, say we have BH3. Okay, so BH3 has 3 hydrogens surrounding it, and this would be the Lewis structure. So when we talk about domains, so each of these bonds around the central atom represent a domain. So this would have 3 domains. And so the question would be is to how would this appear in a 3-dimensional world? Because on paper it looks to be sort of just flattened out triangular, and that in this case that's how it really looks in the 3-dimensional terms. So as we start to add domains in, so if we look at another example, CH4. So if we look at CH4, we see it has 4 bonds around it, and so we would say that this one would have 4 domains. And so as we start to increase domains, we start to cause the molecules to shift in their geometry. And that's because the electron pairs themselves create repulsions. And as you add more electron pairs in, it causes the bond angles to start to decrease in their values. And so the more the domains you have, the tighter these bond angles are going to be. And so there are actually 5 domains that we are going to look at. And so the first one is the 2-electron domain. These are just shorthand notations as to how to figure this out. So in a 2-electron domain, you're basically going to have the central atom bonded to atoms on the outside. In this case here, we have 2 bonds, and this would represent a linear molecular geometry. So you have your electron domain geometry, and then you have your molecular geometry. So the molecular geometry is determined off of the number of domains and how many bonds it has versus how many lone pairs it has. So if you go back and you look at the previous video, we talked about Lewis structures, you'll see in the video that I start to draw these lobes around these lone pairs. So when we start to count the domains, and we were to look at this one specifically, you have 2 bonds, and then you have 2 lone pairs. These add together to make a total of 4 domains. So we'd have to look at the 4 domains, and we'd have to specifically figure out what the geometry is. So now before we go on to this one here, let's look at BH3. All right. So when you have 3 domains, you have 2 different types of geometries that can be in play. You can have the trigonal planar, or you can have bent as the other one. So when we go and we look at the BH3, we can see that it has 3 bonds that go around it. There's no lone pairs. So when I go back in here, I can see that this one has 3 bonds and no lone pairs. So I would say that this has 3 domain geometry, and its molecular geometry is trigonal planar. Now, if we look at the 4th domain, because these next 2 are 4 electron domains. So when you have 4 electron domains, you're going to have 3 different possibilities. So the first one is where you're going to have this configuration. This is tetrahedral. Tetra meaning 4. Tetrahedral. So that's spelled T-E-T-A-T-R-A-H-E-D-R-A-L. The second one is going to have a lone pair on the top, and then you're going to have your three bonds down here. And then the last one, you'll have a lone pair on top, a lone pair here, and then you're going to have your other two bonded atoms here. So as we look at the first one, we see that it has 1, 2, 3, 4 bonds. So the first one for CH4 would be tetrahedral. Now, if we look at the second one, what do you think the second one would be? I haven't gave the name to you yet, have I? But how many of you picked this one? If you picked this one, that's right. This is called bent. And so this would be a bent geometry. And the last one here, this is trigonal pyramidal. All right. So as we start to look at the first three domains, so there's linear, all right, there is trigonal planar, so that's what that group would be referred to as, and then there's tetrahedral. And within these domains, you are going to figure out your molecular geometry for your molecules. So let's look at NH3. That was from previous video. So in the previous video, we determined the Lewis structure to be this. All right. So if we look at this molecule, I'm going to give you a second here. I want you to figure out what domain it is and what its molecular geometry is. Okay, so if you said 4 domains, you are correct. The 4 domains comes from the fact that you have 3 bonds and 1 lone pair. So we look at this in the 4 domain, and we find that the trigonal pyramidal matches up with its molecular geometry. All right, so that's just a few examples of how we go about solving for the domains for the 2, 3, and 4 domains. Now what we're going to talk about are the bond angles in respect to the domains that we have listed here. Now remember, there are 5 domains. We only have 3 here. We're going to work with the other 2 here in just a couple minutes. So, all right, the bond angle. No, you cannot get your protractor out and measure the angle that you drew on paper, so don't try that. You have to just memorize these or know them. So this is 180 degrees, linear, it's a straight line, so it's 180 degrees. When you get into the 3 electron domains, the bond angle for both of these is 120 degrees. And that's the bond angle between. Now notice for me, as you add in the electron domain, one domain, what happened to the bond angle? It went from 180 to 120. So now we're going to add in 4 domains, so the bond angle should go down even more. Now when we get to this one here, this one is 109.5 degrees. Now if you pay attention here, what happens to the number of lone pairs as you go to the right one? You start to increase the lone pairs. Every time you increase a lone pair, you're going to subtract 2.5 degrees from this. And then you'll subtract 2.5 degrees from this. So this one, the bond angle would be here, would be 107 degrees. And then the bond angle here would be 104.5 degrees. So the main thing that you have to understand with this domain is that you start off with 109.5 degrees, that's your standard, and then every time you add a lone pair, you just subtract 2.5 degrees from that. So as you pay attention, as we talked about previously, as you add domains and you add these electron pairs, what happens to the bond angle? They get shorter and shorter and shorter. So there's 2 domains that we want to finish off with here, and that is the 5 electron domain and the 6 electron domain. So for the 5 electron domains, there are 4 different geometries that can be played. There's the first one here, and this is called trigonal bipyramidal. It's called bipyramidal because it's 2 pyramids stacked on top of each other. If you notice here, there's a triangle here, all right, and so you have your pyramid up on top here, all right, and then you have another pyramid on the bottom. So there's two pyramids stacked together. So that will be the first one. The second one is called seesaw. Now this is where you have one lone pair. The third one is called T-shape. This is where you have three elements and then you have two lone pairs. Notice that the lone pairs are increasing. And the last one is called linear. This is where you have three lone pairs. So this is linear. This one was T-shaped. And then this one here was seesaw. What about the geometries here? So the geometry, these have two different geometries or bond angles here. So the bond angle that you see in between this one here in the bottom, this is 90 degrees. And then if you look at the triangle in between here, this is 120 degrees. So you got to remember this, if I bring this out here, this looks like this. So this is 120 degrees. And if I go up and below, this bond angle here is 90 degrees. Now if we go to this one here, it doesn't change. So you have 90 degrees again, and then 120 degrees. And then this one here, same, this one's 90 degrees. And then this one here is 120 degrees. And last but not least, this is a linear structure, so this one here is 180 degrees for its bond angle. So when you get into 5 electron domains, the 5 electron domains really are reflecting on the exceptions rules. All right, some of these others too, but the 5 domains, the 6 domains really go into those higher number of electrons that exceed the octet rule. So if we look at an example, we look at XeF4. All right, so XeF4, you have 1, 2, 3, 4, 5, 6, 7, 8, because this is noble gas. So you have this here. All right. Now I haven't posted the 6 electron domains yet, but if you look at this here, you can see that this example here, you're going to have 1, 2, 3, 4, and you have 2 lone pairs. That's 6 domains. All right, so if I'm going to write below here the 6 electron domains so we can figure out what the geometry is for this structure here. So the first one we have here is the octahedral group. So this is octahedral. So octahedral just means it has 8 sides, and if I can try to draw this here. If you can see 1, 2, and on the back side 3, 4. So that's 4 on top, and then the bottom repeats that. That's where you get your octahedral from. So it has 8 sides to it. And then we have the next one, which is called square pyramidal. So this is where we add in a lone pair. So here we have X up on top, here, here, and then the square is because you see the square here. Now the lone pair is on the bottom here, and then we have one more, which is called the square planar. All right, this is where we have 2 lone pairs. All right, so the lone pair is on top and bottom, and then you have your X and the square in the midpoint here. So you have so this here is square planar, and that is square planar because you see this square here in the center, but it's also along one plane. So if we look at the example for XeF4 and we come down here, it's got 2 lone pairs. So the 2 lone pairs, so that means that this one is square planar. Now, what about the bond angles here? So the bond angles are all 90 degrees for those. It's all 90 degrees for these. And then it's also 90 degrees here. All right, so the bond angle would be 90 degrees for this. And then the same thing for here. They're all 90 degrees. So the square pointer, the 6 electron domain is a little bit easier as far as bonding is concerned, and we have the 5 electron domains here. So let's do another example just to put another problem on the board here. So let's say we have BeCl2. What would be the molecular geometry and the bond angle for that? Well, if we go on the periodic table, we look up Be. All right, Be has 2 valence electrons. So you'd have one on one side and one on the other. You have your chlorine. So you need to draw your dots around the chlorine here. So you have the Lewis structure. How many domains does this have? Well, we have one here and one there. So that's 2 domains. So going back to do 2 domains, that is a molecular geometry that is linear. So this has a linear geometry, and the bond angle would be 180 degrees. So to figure out your domains, you first have to draw the Lewis structure. Then once you draw the Lewis structure, you go back and you look at the different charts that we've drawn here in relation to the domain. And then in the domain, you can go through and figure out, okay, how many lone pairs does it have? And then what would be the geometry for that specific structure. The more practice you do, the better you're going to get at this. Thanks. This is a continuation of the previous video that we were talking about in reference to VSEPR theory, geometry, and Lewis structure. So I want to do a couple extra examples for you. So the first example we're going to do is BRF5. And what we're going to do is draw the Lewis structure and figure out what its molecular geometry is. So just like before, you got to go through the process of counting the valence electrons. So bromine has 7. Now there are 5 fluorines here. So we know that there's going to have 5, 1, 2, 3, 4, 5. So each fluorine has 7. So remember that the fluorine has to have an octet. So here we go. Alright, so this takes care of our octet, and then we have a lone pair at the bottom there. So now the Lewis structure is drawn, everything matches up with the octets from the fluorine. The bromine is an exception to the octet rule. So the question now is how many domains does it have? So it's got 1, 2, 3, 4, 5. So it's got 5 bonding pairs, so it's got 5 bonds, so therefore it's got 5 domains there, but then you have this lone pair. This lone pair counts as an extra domain. So this has 6 electron domains total. So now what is the molecular geometry of this? Well, if you look here, so we find 6 electron domains here. So this has 1 lone pair. So the molecular geometry of this would be square random. All right, so that's example 1. A second example is going to be SF4. All right, again, draw the Lewis structure. So sulfur is going to go in the middle. There's 1, 2, 3, 4, 5, 6 valence electrons around it. Then we have 4 fluorines. So we're going to just go ahead and put 1, 2, 3, 4. Each fluorine has 7 dots around it. Keep the octet for the fluorine. And then the sulfur, well, that's exceeding octet, but we got to make sure it's even. So 2, 4, 6, 8, and then we have the 2 electrons here, which that makes a pair. So we're good. All right. So now how many domains does this have? 1, 2, 3, 4. So 4 bonding pairs plus the lone electron pair. That's 5 electron domains. Now, from 5 electron domains, so which one does it match up here? Well, how many lone pairs does it have? It has 1 lone pair, so we go here. This one's going to be representing a seesaw geometry. Now, there's one more that we're going to do here in reference to the various domains, and that is ClF3. So again, we're going to start off with Cl being in the center. All right, the fluorine's going to be on the outside because you can't have more than 8 valence electrons in the fluorines. So the chlorine has 7, and there's 3 fluorines here. So we're going to bond the 3 fluorines here to the chlorine, and each fluorine has, again, 7 valence electrons. So, all right, so the fluorines the methyl octets are satisfied, and then we look at the 2 lone pairs here. Now, how many domains does this have here? So this has 1, 2, 3. So 3 bonding pairs plus 2 lone pairs. So there's 5 electron domains. All right, and 2 lone pairs. So that represents a T-shaped molecular geometry. So these are 3 examples that have just one central atom. We're going to look at an example where we have multiple centers. And so first thing we're going to do is I'm going to write the formula out, and then we're going to draw the Lewis structure. So this is going to be propanol. So if we want to write the Lewis structure, when we see these formulas written out, it makes it really easy because each of these represents their own respective structure. And so, like for this first one, we have 3 hydrogens attached to this 1 carbon. For the second carbon, you have 2 hydrogens. For this third carbon, you have 2 hydrogens. Plus, you have this oxygen that's bonded to the hydrogen. Now the oxygen has 2 lone pairs with it. So drawing the Lewis structure isn't too technical, but it still has to follow the principles that we talked about with the octet rule, because all of these elements, all carbons and the oxygen, have to have an octet. So now as we start to talk about the Lewis structure and the molecular geometry relating back to that structure, there are going to be 4 centers here. And so when we talk about geometry, we can't just say the entire molecule has a specific geometry. Each individual center has its own geometry. And that's what's tricky here, is that you have to remember that you have to count it just for one specific center. So let's take, for example, this carbon, the second carbon. All right. So if we look at the second carbon and say, okay, how many bonding pairs are there? Or how many domains are there? So there's 1, 2, 3, 4. So it's 4 electron domain. Now, when you look at the 4 electron domain, it has no lone pairs, so we call that a tetrahedral geometry. And if we look at the first and the third carbons, all carbons have the same geometry as that second one does. Now, when we get to the oxygen, it's different, because the oxygen, it still has 1, 2, 3. The oxygen still has 4 electron domains. But the difference here is that it has 2 lone pairs. And so if you look at the geometry here, it's got 2 domains, so 2 bonds and 2 lone pairs. This represents a bit geometry. All right. So when you're dealing with these multiple centers, you got to make sure you pay attention to each individual center and not try to group them all in the same geometry as one. There's one last detail I want to go over. All right. How do you determine if you have 1 domain or 2 domains when you have multiple bonds? So if I draw the Lewis structure for CO2, and I say, okay, how many domains does carbon have? You're going to look at it and you're going to say 1, 2, 3, 4. So it's got to be 4 domains. And I'm going to tell you, no, that's not correct. And you're going to say, why? It's because a single bond, a double bond, and a triple bond only count as 1 domain. That means that if you have CO2, you have 2 double bonds. That means that you only have 2 domains for CO2. So that's the difference of the structure being linear versus something else. In this particular example, CO2 is a linear structure. So anytime you have, again, a single bond, a double bond, or a triple bond, these only count as 1 domain. They do not count as multiple domains. All right, that concludes our VSEPR theory and molecular geometry. Thanks.